Very good morning to all of you. I once again welcome you all to this current video lecture. As we know that from the last video lecture, we already started the second chapter from our syllabus, that is called as the investigation of the molecular structure. So in the last video lecture, we discussed about the basic information or the introduction regarding this chapter. Now in that introduction, we focus upon some important aspects or the important concepts from this chapter, such as what is meant by the refraction, what is meant by the Snell's law, what is meant by the specific refraction, molar refraction, how to calculate this molar refraction, some important concepts like atomic refraction equivalent, refraction, refractive index of the medium. So these type of the simple concepts we already discussed in the last video lecture. Now today, in a continuation to the same point from the last video, we have to again focus upon the important concept from this chapter, and that is called as the molar refraction. So we have to focus in the current today's video lecture how to calculate this molar refraction with the help of the given data. What are the properties or what are the important characteristics of this molar refraction, how it affect on the magnitude of this molar refraction. So all these properties, all these important aspects regarding this molar refraction we have to discuss in a current video lecture. So for this purpose, there are some four different tabular data is there. So we have to consider all these tabular data one by one. So first of all, we know very well that what is by this molar refraction. So this molar refraction is the important characteristics for a particular liquid. That molar refraction we have to calculate. We are interested to calculate this molar refraction. So the question arises, how to calculate this molar refraction in a unit of ml per mole. Before that, we studied one important concept that is called as the atomic refraction equivalent. Now what do you mean by this atomic refraction equivalent? Whenever we want to calculate the molar refraction for a particular liquid, so we have to take into consideration the contribution of each and every atom present in a molecule. So that particular contribution of every atom in a particular molecule, that is called as the atomic refraction equivalent. So the table number 1 is there, in which some constant values of atomic refraction value constants are given. So this is the refraction equivalence for sodium D light. So for this experiment we use the light whose wavelength is a sodium D light is there. So that light we can use here for considering the atomic refraction equivalent. So in this table some values are given for the atom, such as hydrogen atom is there, carbon atom is there, then oxygen present in a carbonyl group, and oxygen atom present in a hydroxyl group. So these four values we take here for our simplification for considering or for studying this atomic refraction equivalents. Now if we look towards their magnitude, this hydrogen has the value of 1.100. It is called as its atomic refraction equivalent. For this carbon atom, the atomic refraction value is a 2.418, while if we consider the third important atom in a molecule, that is called as oxygen. Now this oxygen may be present in a different functional groups. Now if this oxygen is present in a functional group called as a carbonyl, that is a C double bond O, then its atomic refraction value is a 2.211. On the other hand, if a same oxygen group is present in a hydroxyl functional group, if it is present in a OH functional group, then its atomic refraction value is a different, and that is equal to the 1.522. So we can say that these are some common atomic refraction equivalence values for some atoms. Now what is the importance of these values? So by using these values we may calculate the molar refraction for a particular molecule. For example, if we want to calculate now molar refraction values for this methyl alcohol, suppose if methyl alcohol is there, CH-3OH. So for this methyl alcohol, if we want to calculate its molar refraction values, then how to calculate it? So before calculating its molar refraction, we have to count how many number of different atoms are present and their actual numbers. So in a methyl alcohol, how many atoms is there? One atom is a carbon, second type of atom is a hydrogen, and third type of atom is a oxygen. Now after deciding this, how many number of carbons, hydrogens and oxygen is there? So carbon is present 1 in number, hydrogen is present 4 in number and oxygen is present in a 1 in number. So we can say that after counting all the atoms of carbons, hydrogens and oxygens, after that we have to multiply the number of carbons, number of hydrogens and number of oxygens by the respective value of their atomic refraction equivalents. So in this case what happens? The atomic refraction value for this carbon is equal to 2.418. So it is equal to the number of carbon atom is equal to 1. So 1 multiplied by 2.418 plus second value is there for this hydrogen. How many hydrogen is present? It is equal to 4. So again this 4 multiplied by its atomic refraction value is a 1.100. Again the last atom is present, that is called as oxygen. Now this oxygen is present in the form of OH, that is a hydroxyl group. So we have to take the value not for its carbonyl. So that value is equal to 1.522. So if I consider all these atomic refraction equivalents value and if we add together all this contribution, then the final value for this molar refraction of this methyl alcohol comes to be 8.218. So we can say that the molar refraction for this methyl alcohol is a 8.218. And how it is occur? It is obtained by the addition of contribution of each and every atom, that is this carbon, hydrogen and oxygen. So if we add together all these atomic refraction equivalents value, that value comes out to be 8.218 in a ml per mole. So this is a very important application of this atomic refraction equivalent in order to calculate the molar refraction for a particular liquid. So in this way we may calculate now molar refraction for this ethyl alcohol, propyl alcohol or butanol or any type of the liquid compound by using this constant data, that is called as their atomic refraction values. So by using this table number 1, we are familiarized with what is my atomic refraction equivalents and how to calculate molar refraction by using that particular constant values. Now after studying this type of the simple calculation of this molar refraction, next we have to consider what are the important characteristics of this molar refraction. Whenever we can say that molar refraction of the given liquid is so and so, so what are the important properties, what are the important characteristics of this molar refraction, that we have to discuss now. So whenever this molar refraction is concerned, this molar refraction property is called as the partly additive and partly constitutive. These two important properties of this molar refraction is there. This property is called as a partly additive and partly constitutive. Now nextly we are interested to understand what is by additive and what is by constitutive. So for this purpose now we have to consider this table number 2. We have to consider this table number 2 for understanding the property of this molar refraction, that is it is called as a partly additive. This property is called as the partly additive property. Partly additive property. Now we are interested to understand what is by this additive property. So for this purpose we can use this type of tabular data in the table number 2, in which what is given, series is there. Now this series is for a similar type of the organic compounds. So we take here alcohol series. We take here alcohol series. In the second column the molar refraction values is given, and in the last column the difference between the two different compounds molar refraction values is given in the third column, that is called as the delta rem. Now in the first column we take one series, and what is that series? That series is called as the homologous series for the alcohol. Is all these examples are called as the homologous of each other of alcohol family. So what we can take here? We take here example of alcohol one by one. So all these examples get differ by the CH2 unit. CH2 unit difference is there in their molecular formula. So all these examples are called as the homologous of each other, and this series is called as the homologous series. Now our interest is to know what is the magnitude of molar refraction for each and every organic compound. So first of all, if we look toward the first example from this series, it is called as a methyl alcohol. What is the value for this molar refraction for methyl alcohol? It is a 8.218. Secondly, if we look towards the second example, that is the ethyl alcohol, its value is a 12.73. So in this way 4 different alcohols are given and their respective molar refraction values are given. Now we are interested to understand what is in by additive property. Molar refraction is called as a partly additive property. So what is by additive? So we know that all these examples are called as a homologous of each other. They get differ by the CH2 unit in their molecular formula. So now if we look towards this molar refraction values, and the last column is a difference. Now if we take the difference in between the two continuous example from a given series, that difference is the difference between the molar refraction of methyl alcohol and ethyl alcohol. What is the difference? Is that difference is equal to 4.512. So we can say that these two molar refraction values of methyl alcohol and ethyl alcohol has the difference of 4.512. Next, if we take the difference between this ethyl alcohol's molar refraction and propyl alcohol molar refraction value, that difference is again obtained is equal to 4.78. And at the last, if we take the difference between molar refraction of propyl alcohol and butyl alcohol, that difference occurs equal to 4.62. So by observing all the differencing values between the molar refraction of the continuous examples of this alcohol, what we can say that we can say that all these values have the constant difference between the molar refraction values. This is a near about constant difference, 4.5, 4.7, 4.6. So we can say that no doubt the molar refraction values is a different of different alcohols, but at the same time the difference between the molar refraction of the two continuous alcohols is fairly remains constant, and that's why we can say that this molar refraction value is called as the partly additive property. No doubt the value or the magnitude of molar refraction going on increasing, but at the same time the difference between the molar refraction of the two continuous examples remain a constant, and that's why this property, that is the molar refraction property, is called as the partly additive. This is a partly additive is there. So this is one of the important characteristics of this molar refraction. Next, the second important property is there for this molar refraction, that as well as if this property is called as the partly additive, at the same time this property is also called as the partly constitutive. This property is called as partly constitutive. This property is called as a partly constitutive. This property is again called as partly constitutive. First of all, we already discussed here what is partly additive. At the same time, this property is again called as partly constitutive. And what is by constitutive? So for this purpose, we take a tabular data from this table number 4. So in the first column, some compounds are given. Next, in the next column, their proper structure is there, and at the last column, their actual value of molar refraction is there. So first of all, if we look towards the first column, that is the name of the compound. So first compound we take here for our discussion is called as allyl alcohol. This allyl alcohol is the first compound is there. What is the structure for this allyl alcohol? So that structure is a CH2 double bond CH single bond CH2 OH. So we can say that this example is called as a alcoholic compound. The second compound is there, that is called as the propylaldehyde. This compound is called as a propylaldehyde. So what is the structure for this propylaldehyde? It is a CH3 CH2 single bond CHO. So we can say that first compound is the alcohol, second compound is the aldehyde. These two compounds are called as the isomers of each other, means they have the same molecular formula but they have the different functional or different structural formula. So this is called as the isomers of each other. Now we are interested to study their magnitude of molar refraction. So what is that magnitude? So for the first compound, that is the allyl alcohol, refraction value that is equal to the this 17.112, that is 17.112, and for this second compound, that is called as the propylaldehyde, the value is equal to the 16.065. 16.065. Now if we look towards the last column, that is the magnitude of this molar refraction, the magnitude for this first compound, that is the magnitude of molar refraction for allyl alcohol is more than that of the propylaldehyde. And why this is so? So for this we have to consider what is by this constitutive property. So constitutive means construction. What is the construction of this molecule? So if we look towards now the difference between these two compound structure, the first difference is that first has the OH functional group, second has the CHO functional group. At the same time, this first compound has carbon-carbon double bond. This first compound has a carbon-carbon double bond, but this double bond is absent in this second compound. So we can say that this first compound has the conjugation, while the second compound cannot have the conjugation. So we can say that this type of nature is called as a constitutive nature, and due to this type of constitutive nature, what happens? The magnitude of the molar refraction values get altered. So we can say that whenever a liquid compound contains conjugation, then its molar refraction value is get altered. Its molar refraction values get or it affects its molar refraction values due to the presence of this carbon-carbon double bond. And so we can say that this property is called as a partly constitutive property. This is called as the partly constitutive property, means for the same isomers, the value of this molar refraction is get affected due to the presence of such a type of double bond. Sometimes it may be the triple bond. So for this purpose, this property is called as the partly constitutive property. So these are the two important characteristics of this molar refraction, that it is called as the partly additive as well as partly constitutive property. So these are the two important properties. Next, again, if we consider the next angle of this molar refraction, suppose if we discuss the liquids, and for the liquids, if we discuss their molar refraction values, so for this purpose, suppose in this table number third, if we consider the two different compounds, one is called as a diallyl compound and second is called as the isodiallyl compound. These two compounds is there. Again, these two compounds are called as the isomers of each other. Means again they get different in the case of their particular structures. So this diallyl compound is there. It has the structure of CH2 double bond CH, single bond CH2, CH2 single bond CH double bond CH2. While the second compound is there, isodiallyl. In this case, the structure is a CH3 single bond CH, double bond CH, single bond CH, double bond CH, single bond CH3. Now, what is the difference between these two structures? So, first compound, there is a absence of conjugation. The conjugation is absent, while in the second compound, the conjugation is present. Now, how this conjugation affects on the magnitude of this molar refraction, so that we have to consider. Now, for this first compound diallyl, if you take into consideration two magnitudes of this molar refraction, one by calculation and second by observed, that is by experimental methods, the value for this molar refraction by calculation is equal to 28.78, while by observed it is also 28.78. So we can say that for this diallyl compound, the magnitude of molar refraction both by calculation by experiment is equal to same, that is a 28.78. So these two values are exactly equal to each other. On the other hand, if we consider second compound, that is isodiallyl, so for this isodiallyl, the value of molar refraction by this calculation obtained as 28.78, while the experimental value is equal to the 29.87. So there are two different values are obtained for the second compound, that is for isodiallyl. Now why this is so? This is due to the presence of such a type of the conjugation in the structure. So we can say that whenever such a type of conjugation is present in a given isomeric compounds, no doubt their calculated values are equal, but their experimental or the observed values get altered. So this is a important aspects of a conjugation present in a molecule. So we can say that if in a given liquid, if conjugation is present, then there is a change in its molar refraction values is obtained. In this case, the observed values are higher as that of the calculated value, and such a type of anomalous behavior or anomalous increase in a particular molar refraction values of a liquid by the presence of this conjugation, then that property is called as the optical exaltation. This is called as the optical exaltation. This important property is there, optical exaltation. So what is optical exaltation? For the liquid compounds, if there is an increase in a molar refraction values, that is the observed molar refraction values obtained due to the presence of such a type of conjugation, then that property is called as the optical exaltation. And this is a very important test for a given liquid. If suppose there is a difference in these two calculated and observed values is obtained, we indirectly say that that liquid compound must have the conjugation in its structure. So this is a important data in the table number this 3 is there. So by considering these four different tabular data, first, second, third and fourth, we discuss the four different properties of a particular molar refraction. In the first tabular data, we discuss what is by this atomic refraction equivalents. In the second data, we consider what is by additive property, why molar refraction is called as a additive property. In the table number 4, we study what is meant by partly constitutive property, that is a molar refraction, why it is called as a partly constitutive. And in the last table, that is the table number 3, we consider what is meant by the optical exaltation of a liquid, or what is the anomalous behavior is obtained due to the presence of such a type of the conjugation. So this is regarding the molar refraction. Now we consider all these examples regarding these liquids. We all these all examples we consider here liquids only. So for these liquids we can easily calculate molar refraction by considering such a type of the tabular data or the given constant values. Nextly, now suppose if we want to calculate molar refraction for gases, if we want to calculate molar refraction for gases, so how to calculate that? So for that gases, the molar refraction values are exactly similar to that of their liquids value. The liquids and these gases have the near about same values for its molar refraction. But now suppose if we want to calculate this molar refraction, if we can calculate, if we want to calculate the molar refraction for solids, suppose if we want to calculate the molar refraction, so how to calculate that? For solids, how to calculate this molar refraction? So for this purpose, what we have to take into consideration, our aim is to calculate molar refraction for solids. So how to calculate that? So first of all, we have to convert that solids, or we have to convert that solute into a particular solution. We have to convert that that solids or solute into a particular solution state. So for this purpose, what we have to take here, we have to choose a proper solvent for the formation of a solution. So we take a solute, a proper solvent. By combining all these two parameters together, we obtain a solution. After forming that solution, we may now use some relationship, some mathematical equations to solve or to calculate this molar refraction. So for this purpose, we have to take into consideration some constant or some physical parameters of a particular liquids. So for this purpose, we take here a simple equation: R1, 2 is equal to, this R1, 2 is equal to, now what is by this capital R? R stands for this molar refraction 1, 2. So this is a R1, 2 stands for molar refraction for the solution, 1 for solvent, and this 2 stands for the solute. So R1, 2 is equal to, it is equal to n square minus 1, n square minus 1 upon n square plus 2 into n1 into m1 plus n2 into m2 divided by small d. So this is the first simple equation is there. R1, 2 is equal to n square minus 1 upon n square plus 2 into n1 into m1 plus n2 into m2 divided by d. Now what are the simple parameters in this given equation? We know this R is a molar refraction for a solution. This small n stands for atomic refraction equivalent. Sorry, this is called as the refractive index of the medium. This n stands for refractive index of the medium. This capital M1, capital M2, this is called as the molecular weight of a solvent and solute respectively. M1 and M2 is called as the molecular weight of solvent and solute respectively. This N1 and N2, what is by this N1 and N2? N1 and N2 is called as the mole fraction. This is a mole fraction of solvent and solute respectively. And this D stands for density of a particular solution. Now this is the first simple equation. Now the same molar refraction of a solution may be correlate with that of the molar refraction of solvent and solute. By the next equation, we may write here R1, 2 is equal to N1 into R1 plus N2 into R2. This is the next relationship between the molar refraction of a solution to that of the molar refraction of a solvent and solute. So what is the changes in this second equation? R1, 2 is equal to N1 into R1 and plus N2 into R2. Now in this equation, two terms is there. One is called as R1 and second is called as the R2. What is by R1 and R2? This R1 stands for molar refraction of a solvent. This R1 is called as the molar refraction of a solvent, and this R2 is called as the molar refraction of the solute. And how it is obtained? It is obtained by the above equation. This R1 is equal to, what is the value for this R1 from the above equation? We may write here this R1 is equal to n square minus 1 upon n square plus 2 into, what is the next? It is equal to the m1 divided by d. So this is the value of this R1 from the equation number first. R1 is equal to n square minus 1 upon n square plus 2 into m1 upon d. In the same way that R2 may be equal to, R2 is equal to n square minus 1 upon n square plus 2 into, instead of m1 we take here m2 divided by D. So this is the next equation, by that is a relationship between the molar refraction of a solution to that of the molar refraction of a solute and solvent. Now from this given equation, if suppose we are interested to calculate the molar refraction for solutes, for solute we have to calculate the molar refraction. So if we know the magnitude of this R1, if we know the magnitude of this R1, that is a molar refraction of a solvent, at that condition we may calculate this R2, that is called as the molar refraction of a solute. So for this purpose the above equation becomes R2 is equal to, that is a R2 is equal to R1 comma 2 minus N1 into R1 divided by, that is a N2. So by using this simple equation, we may calculate here molar refraction of a solute, that is R2 is equal to R1 comma 2 minus N1 into R divided by N2. So this is a simple equation. By using that simple equation, we can calculate the molar refraction of a solute by converting into its solution state, and after considering this type of the simple parameters, we can calculate its molar refraction in a unit of ml per mole. So in the today's video lecture, we consider the different aspects of this molar refraction. What is meant by atomic refraction equivalence? By using this atomic refraction equivalence, how to calculate molar refraction? What is by additive property? What is by constitutive property? Then how this molar refraction get altered with the presence of the conjugation, that is we consider here an important property that is called as the optical exaltation. At the last we consider how to calculate this molar refraction for solids by considering this type of the different physical parameters. So at the last we derive one simple equation for calculation of this R2. So these are the important aspects of this molar refraction. So with this today I can stop here. The remaining portion from the given topic we will study in a upcoming video lecture. So with this I stop here. Thank you so much.